Okay, 7 o'clock. So let's go ahead and get started. So how's everybody doing? It's our first lecture after the spring break. So hopefully everyone had a restful spring break. But I know some of you at least were working on some stuff. But hopefully, at the very least, you guys have been staying safe and you're able to rest at least a little bit. At least catch your breath from all the craziness going on. So anyone want to share kind of some fun things they did over spring break in your home, hopefully? Nice. Yeah, worked on your thesis. That's a good thing. Very good thing. Nice. Calligraphy. That's awesome. Sleep is always good. Oh man, I'm sorry about that. Yeah, everything's being canceled, so a ton of plans are getting canceled. But hopefully you can go. When things are opening up again. Yeah, for me, I did a lot of work. So actually, I tried to kind of get ahead as much as I could on the prep. But besides that, I played a lot of video games. So there's I have a really big backlog of video games that I've been meaning to play for a long time. So I got to play a lot of that. So I'm very happy. So I play this series called the Legend of Heroes. So there's a fan translation of one of the games that came out recently. I play on PC. I was able to sink like 70 hours of it over the spring break in total. So I was very happy. So under many circumstances, I don't get to play that much games. So it was a nice silver lining to the quarantine that we have. No Overwatch. PvP games make me lose my mind. So I played League when I was in college, and my mental health suffered significantly for it. So ever since then, I've kind of said no more PvP games. Okay. So hopefully, everyone's doing well, everyone's staying healthy. So let's get started for today. So I have a few announcements kind of before we get started with the lesson. I think we had a tiny little bit of boundary layers to finish up. We had one more example, and then we're going to launch into our new topic, which is vorticity. So the first announcement I want to make is that I did spend some time over spring break prepping some stuff. So since we have this kind of virtual instruction for the rest of the semester, and I know a lot of you have health and family things to take care of. So kind of my goal for the rest of the semester is to basically give you guys as much flexibility as you can to kind of tackle the content kind of at your own pace and when you have time available to you. So what I did over the spring break was I tried to get basically 3 weeks worth of content up on Titanium. So basically, if you look on there, you'll see the lecture notes for this week, which is vorticity. You'll see the review for the midterm, which is going to be soon, and then the topic after that, which is fluid instability. So there's basically going to be 3 weeks worth of content that's available there for you to see. Okay. So I'm going to try to kind of finish up. So we have kind of after instabilities, we have one final big unit on turbulence. So I'm going to be working on that throughout this week and probably early next week. So I'll try to get that up basically as soon as I can. So you can, have the lecture notes kind of as early as you can, so you can look at it, whenever you have time. Because I know everyone's schedule is really uncertain right now. So I want to be as flexible as I can. So the other thing is for the midterm. So I have a few announcements on that. So just like we did for the first midterm, we're going to have a review session. So the review session is scheduled for next Monday. So we're going to have the same format as before, where I'm going to put a poll on Titanium where you guys can kind of vote for the topics that you want to see. And then we'll try to cover as much as we can for the midterm. Right? I've already posted the study guide for the second midterm, so that's going to be online. So if you check that out, you should see that the midterm is not going to be cumulative. So it's basically going to be covering just the stuff since the first midterm. So just a quick rundown of the topics. It's going to be lubrication theory, boundary layers, and then what we're going to cover this week, which is vorticity. Okay. So of course, a lot of the stuff from earlier they kind of factor in, but it's not going to be, especially like Navier-Stokes, but it's not going to be purely any problems on the first unit of the class. Okay. The other announcement I want to make is that the midterm, I'm going to push back the midterm by one class session. So originally, I think it was scheduled for next Wednesday, but just so you know, we have time after the review session, and you have a week to study after that. I want to make sure I give you guys that time. So the midterm is going to be 2 weeks from today. So it's going to be the Monday of week 14, I think it is. So we talked about this briefly before the spring break, but the format of the midterm is going to be, I'm going to upload the midterm onto Titanium basically at 7 p.m. on that Monday, 2 weeks from now. And then you're going to have 24 hours to basically finish the exam and put it back. So I was kind of doing some thinking over the spring break about, you know, how the extra time is going to factor into the exam. And in the end, I decided, you know, I'm not going to change I'm basically going to give you the exact same exam that I would have given you if we had basically just an hour and 15 in the class. So I'm not going to make it intentionally any harder or any longer than kind of that exam. So, you know, it should kind of take you the same amount of time as you know, as you did in the class. Of course, you know, you'll have the all your notes, and you'll have, you know, the book available to you. So basically, you'll definitely make use of that. Mostly just because I can't police it, so I can't tell you to not do it, because then there's no way for me to watch you guys to do it. So, you know, make use of your notes, make use of your book. But at the same time, you know, I think it's still worth it to make your cheat sheet just as a study tool. And you know, I know this is just personal for me, but I personally like to, you know, after going over weeks and weeks of content, to kind of you know, pare that down into just a page of notes, and to kind of see that and be like, wow, you know, that's kind of nice. For me, that's something that I personally enjoy, but I know that's just me. But it's besides that, I know it's a good study tool. So definitely make sure to do that. Okay? Right. So the question is, are we going to post the pic of the solution? So if you can scan it, if you can scan the you know, your work with your phone and upload a PDF, that's kind of the format that works best for me. So you can take pictures if you don't have the app on your phone to do the scanning. That's fine with me. But if you can put it into a single PDF, that kind of works the best. Yeah. So you would basically just upload it, and I would grade it, and I would give you the feedback from there. Okay. Okay, and then one more, and then besides that, we have I put an additional homework. So some of you have noticed it already, so because some of you have asked questions about it over the spring break. But I want to make sure I give you guys some practice with the Vorticity stuff that we're going to cover this week. So homework 5 is posted on Titanium, and it's going to be due a week from today. So it's going to be due next Monday. Okay? All right, so the question is, for homework 5 problems 2C and 2D, do you have to make plots? So for 2C and 2D, you know, if you look at the homework, then I ask you guys to make some plots. So that's basically just for you. So there's you don't have to make the plots for the homework. But the plots do help you out quite a bit in you know, and finding out you know, what those questions are asking for. So you don't have to print those out, or you don't have to submit it with your homeworks, but it does help quite a bit with those problems. But you don't have to submit it. Yeah. All right, are there any questions? Oh, so the question is, what is the range of X and H? Let's answer kind of homework specific questions kind of in office hours, because I kind of, you know, I kind of want to get into the lesson a little bit sooner today. Okay. All right, so problem 2, yeah. So let's do that on Wednesday, because I want to make sure I finish the boundary layer stuff and at least cover enough to get you started on problem 3 on the homework 5. So let's save kind of the homework questions for Wednesday. Oh, no problem. I mean, it's you know, you know, there was a lot of announcements today. So normally, you know, we have time to do it, to go over homework problems at the beginning, but just today there was a lot of announcements. So let's save it for Wednesday. Right. Any other quick questions I can answer about the midterm or the homeworks, or just anything going forward? Okay. So let's pick up where we left off. So if you remember from before spring break, we were going over Thwaites method, which is a method to solve for the momentum thickness, the displacement thickness, the wall shear stress and separation in a boundary layer, right? Because remember, what we said was, if we're trying to use an analytical approach with the Blasi solution, it's normally really difficult to get all the quantities that you want. So Thwaites method was kind of invented to kind of an easier. So let's look at this example. So in this example, we have a diffuser. Okay. So diffuser is nothing more than just a diverging cone. Okay. So it looks something like this. So we have flow coming in. Our flow has a velocity of u naught. Okay. And then the way that this diffuser is designed, so a diffuser is usually designed to slow down flow. So by the end of the diffuser, the free stream velocity will be half. Okay. Okay. And then one other thing that we know is that the length of this diffuser is given by L. Okay. And so what we're interested in is that, just like any kind of solid surface, whenever we have flow over it, we have a boundary layer that's going to form. Okay. Okay. And then what we want to do is we're going to use Thwaites method to determine if the boundary layer is going to separate. Okay. Okay. So if you remember from Thwaites method, we have this correlation parameter lambda. Okay. So if the lambda ever gets less than, I think, 0.09, 0.09, 0.9, okay. So if we ever reach a lambda coefficient or lambda value of less than 0.09, then our boundary layer will separate. Okay. So in order to do this, we basically need to get an expression from lambda. So lambda from before is given by this expression here. Okay. So it's going to be theta squared over nu times d ue dx. Okay. Where this theta right here, this theta is our momentum thickness. Okay. And this due dx, this is the change of the free stream velocity as a function of x. Okay. Okay. So in order to compute this this lambda, we're going to need this, and then we're going to need this. Okay. So we're going to use basically the parameters of the problem and our formula for the momentum thickness to compute those two quantities, and then compute lambda. Okay. All right. Any questions on the problem setup before I wipe the board? Okay. All right. So first, let's work on UE. Okay. So for UE, we basically need to come up with a functional expression to basically express how UE changes with X. Okay. So to do that, we're going to use basic conservation of mass. Okay. So since we have a confined space, we can basically say that the flow rate is going to be constant. Okay. So basically what we can say is that U0, A0, okay, where this product of U0, A0, this is the flow rate at the inlet. Okay. This is going to be equal to the product of UE of X times A of X. Okay. So this is the flow rate at basically any other location within the diffuser. And so in order to solve for this, we know U0 and we know A0. Okay. So the other thing we don't know is A of X. Okay. So if we assume, just based on kind of the shape of the diffuser that was given in the previous figure, that this A of X is a linear function. Right, so A of X is equal to mx plus b. Okay. We can basically solve for m and b, based on the parameters in the problem. Okay. So let's plug in some conditions on this. So we know that the area at x is equal to 0. This is going to be a naught. Okay. So if we plug in x is equal to 0 in our expression here, we have m times 0 plus b. Okay. So this tells us that b is equal to a naught. Okay. Right. And so the other piece of information we know is that because we know the velocity has to basically be half at the end of the diffuser, we know that at x is equal to L, our area is going to be double what it was at the inlet. So area at x is equal to L is equal to 2A. Okay. So we plug that in. Okay. So we have m times L plus b. We know what b is. Okay. So this tells us that m is equal to A naught over L. Okay. So if we plug those in for A, we get A of X is equal to A naught times X over L plus 1. Okay. So that we plug this into our UE equation, so we can solve for UE, then we get UE is equal to U naught all over 1 plus X over L. Okay. So there we have an expression for the free stream velocity as a function of X that we can use both the equation for the momentum thickness and for the to take the derivative to find the lambda parameter. Okay. All right, any questions on this before I wipe the board? Okay. Okay, so now that we have UE, we can find the momentum thickness. Okay. So momentum thickness, if you remember from our Thwaites method before, was given by this long expression here. Okay. So we have theta squared is equal to 0.45 nu. Okay. We're going to divide by U naught. Okay. And at this point, we plug in UE to the 6th power, right? And then we take the integral of 1 over 1 plus X over L to the 5th. Okay. So basically, we're plugging in a UE over there. Okay. Right. Plus our initial momentum thickness. So this is going to be theta naught times squared times 1 plus X over L to the 6th. Okay. Right. It's to the 6th power, not to B. Sorry. Yeah, there's no B here, so it's a 6. Yeah. So basically, what I did was I think in the original Thwaites equation you have UE to the 6th power here. Right. So since we have our expression for UE, then we basically plug in that expression for that. Okay. I think it's 0.45 nu over UE to the 6th, and then you integrate UE to the 5th right there. So yeah, you plug in the stuff, and then this is kind of what you end up with for the Thwaites method. But it's basically just kind of plug and chug for this part. Okay. So this is kind of a nasty integral. So I'll kind of put on or kind of wave my hands in the air and just say that we perform this integration. Okay. And then what we get is the following. So we get theta squared is equal to 0.45 nu all over U naught times 1 plus x over L to the 6th times L over 4 times 1 minus 1 plus x over L to the minus 4, okay, plus theta naught squared times 1 plus x over L to the 6th. Okay. Okay. So now that we have theta, and now that we have UE, we can basically plug in and solve for lambda. Okay. So remember, lambda is equal to theta squared over nu times d UE dx. Okay. So if we do that, then we get the following. Okay, we get minus 0.45 divided by 4 times 1 plus x over L to the 4th power minus 1 minus theta naught squared. We put that on the next line. Oops, shoot. I hit the wrong button. Sorry about that, technical difficulties. So let's write that again. So we have lambda is equal to minus 0.45 divided by 4 times 1 plus x over L to the 4th power minus 1 minus theta naught squared U naught over nu times L times 1 plus x over L raised to the 4th power. Okay. Right. So at this location, we have a fairly complicated expression for lambda. Okay, because we have some x's and stuff like that. So this is if you kind of looked ahead on the homework, it's at this point I kind of recommend that you plot this function just to kind of help you out. Okay. Okay. Right. But let's kind of look at this kind of analytically and just see, because remember we're going to get boundary layer separation if this ever reaches below minus 0.09. Okay. So if we take kind of the best case scenario where theta naught's equal to 0, okay. Okay, so that's kind of our best case scenario. We still get a function that kind of monotonically decreases with x. Okay. So eventually, you know, this function will basically reach a point where it's going to be less than negative 0.09. Okay. So eventually, we're going to get boundary layer separation. Okay. So the question is when. So we can solve for that if we set okay. So we can solve for that location by setting lambda is equal to minus 0.09 and then solving for x. So if you do that, we get x is equal to 0.158 times L. Okay. So you can see it, you know, that that the boundary layer separation will occur at only when we're about 16% through the diffuser. So this, we can say that for sure that this boundary layer is going to separate. Okay. So the tempting thing here is to say that, you know, this is kind of the location where the boundary layer will separate. So it's going to separate exactly 15.8% into the diffuser. So it's very tempting, but you have to kind of temper your temptations, because remember, the way that we got through this equation was we did a lot of integration, right? So we took our boundary layer equations and we integrated it basically over the boundary layer, and then we applied a lot of experimental data to get to this point. So for a lot of cases, this usually using Thwaites method is not enough to tell you exactly where the boundary layer will separate, but it can tell you if it will separate. So from this analysis, we can say that if that separation will definitely occur, we just don't know where exactly it's going to occur. Right. So the question is, if x is less than L, we know separation will occur. Yeah. So since this x is less than L, then we know that separation is going to occur. And in fact, since this is much less than L, it's only 15.8% of it, then we know for sure that somewhere in the diffuser that this is going to, the boundary layer is going to separate. But remember, this is not enough information to tell you where, but it can tell you if the boundary layer is going to separate. Okay. All right. Any questions on this example before we move on to vorticity? Okay. So let's go ahead and move on. Okay, so we're going to move on to the next topic. So this is the last topic that's going to be on the midterm. So that's going to be vorticity. Okay. So we've seen vorticity before, so we at least have some, you know, understanding about what it is. So let's kind of, you know, I wanted to kind of take a little bit of a deeper dive because it's, you know, it's something that's really important to kind of fluids in general, and more importantly, it's going to be important for turbulence. So the turbulence unit is kind of like the coup de grace of kind of this class. So it's you know, it brings together a lot of important stuff. So to kind of understand some topics in turbulence, we kind of need to know a bit more about vorticity. So that's kind of the motivation behind this. Okay? So let's start with just some basic definitions. So vorticity, as we know, it's a measure kind of the amount of twisting or the amount of rotation that a fluid goes. Okay? So if we can put a definition on this, this is a measure of the instantaneous rotation of a fluid particle. So it's basically just a way for us to quantify the amount of rotation that a fluid does, because, you know, it happens quite often that fluids will rotate. You know, we've all seen kind of whirlpools that kind of happen in nature, and they're, you know, pretty awesome. But even on kind of a micro scale, so if you have kind of turbulent flow, what tends to happen is you have these kind of small, we call them eddies, turbulent eddies. You know, and those are kind of very important structures for turbulence and kind of for a lot of fluid mechanics. Okay. And so the way that we compute it is we take a cross product, right? So we say that omega, okay, which is a vector, where this is our vorticity. This is going to be equal to the cross product of our nabla and velocity. Okay. So this is our velocity. And And by taking this cross product here, what we're taking is the curl. Okay. So the curl is probably a mathematical operator you've heard of before. So to get vorticity, we basically just take the curl of velocity. Okay. And so the key kind of thing to note here is that this vorticity is also a vector. Okay. Because that's kind of a property of cross products. So cross products, you take the cross of two vectors and you get a vector in return. Okay. And then the direction of the vorticity is important. Okay. So the vorticity vector is always going to point in the direction of the axis of rotation. Okay. So in the case, say we have kind of a rotating flow. Okay. So we have a flow that rotates like this. Okay. Then the vorticity vector is going to point perpendicular to this. Okay. Just like that. So if you think of kind of like a spinning top, then the vorticity vector points kind of in that direction of the top points. Okay. Right. And then just like any quantity with a cross product in mathematics, the way that we can determine, because this can, because we know that this vector can either point up or it can point down. Okay. And so the way that we determine whether it kind of goes up or down is we use the right hand rule. So by using the right-hand rule, you can determine which way that the velocity vector or vorticity vector goes. Okay. So that's not going to be too important for what we're doing, but that's just kind of trivia for you guys if you're curious. All right, any questions on kind of some of the basic definitions before we move on to some applications? Okay. Okay, so where is vorticity important? Okay, so it's important in aerodynamics. Okay. So if you've ever kind of looked at the flow that comes off the edge of a wingtip, okay. Okay, so there's the end of my wingtip, and so because of this airplane's in the air, we need lift to kind of bring it up in the air. We tend to have high pressure air or high pressure fluid on the bottom and low pressure fluid on the top. Okay. And then what tends to happen is that because you have a high pressure on the bottom and low pressure on the top, the air kind of pushes itself and forms what's called trailing vortices. So if you've kind of seen some cartoons about flying stuff that flies, like Peanuts, like the old Peanuts cartoons, you might see these kind of patterns in those cartoons. So those weren't just things that the artist drew. So this was this actually happens because what tends to happen when you have flying objects is you have these trailing vortices. So you basically have little pockets of rotating air that kind of falls off the end of a flying object, and the properties of those trailing vortices is something that's really important for the study of aerodynamics. So we won't get into it too much in this class, just because that's more of an inviscid flow aerodynamics thing, but it's it's something that's really cool and really cool to see. So another area of fluids where vorticity is important is in weather modeling. Okay. So there's a lot of really complex computational fluids that goes into predicting the weather each day, predicting the the path and the damage of like hurricanes and typhoons. So vorticity is something that's really important there. So if that's something that's interesting to you, like environmental fluid mechanics, then you'll be seeing a lot of vorticity. That's for sure. Okay. All right, and then probably the most important thing is or for us, is its applications to turbulence. Okay. So in turbulent flow, we know that's very chaotic in nature. What tends to happen is that there's tons of like tiny vortices that tends to get generated and kind of move with the flow. Okay? And so what we'll see is that, examining, when we examine kind of the relative size of these vortices, that's something that's going to be really important. Okay. In particular, when we get to turbulence, we'll learn about something called the energy cascade. It's kind of a muted E. Sorry, my iPad is being very unruly today. Okay, so that's the energy cascade. And we'll see that kind of the vorticity is something that's going to be really important to know for that. Okay. All right. So even though vorticity, it's kind of a little bit more difficult to visualize than velocity in general. Usually people have more difficulty kind of drawing it and visualizing it. It's something that has really central importance to fluid mechanics. In very many aspects. Okay. So let's go over some kinematics of vorticity. Okay. So the first thing that we'll go over is vortex lines. Okay. So these are kind of the analogous kind of structure to streamlines. Okay. Because you remember for up to this point, we've been dealing a lot with the velocity. So in order to visualize the velocity, we visualize them with streamlines. Okay. So if you remember kind of the definition of streamlines, we know that everywhere the streamlines are going to be tangential to the velocity. Okay. Okay. So vortex lines are kind of the analogous structure for this. So the vortex lines, they're basically lines that you can draw in the flow, and then everywhere they're going to be tangential to the vorticity. So it's, you kind of think of them as the same as streamlines, but instead of being tangential to the velocity, we're going to be tangential to the vorticity. Okay. All right, any questions on this board before I wipe it? Okay. Okay, so so for most of this class, we're going to be dealing with mostly just two-dimensional flow. So for two-dimensional flow, the vorticity can either go into the page or out of the page. Okay. Okay. Because we know that the vorticity always has to be perpendicular to the velocity. So if you have a velocity in the two-dimensional plane that looks like this, okay, then we know the vorticity or the vortex lines are always going to come out of the page like this. Okay. So this would be a great application for 3D vision, but the technology is not there yet. But you can imagine each of those, little dots are, it's a vector that's basically coming out at you. Okay. All right. So that's kind of the result of two-dimensional flow. But as you can imagine, for 3D flow, you know, the vorticity can exhibit kind of very complex patterns, you know, basically just as the same as velocity. Right? But for the case for 2D flow, vorticity is going to be either into the page or out of the page. Okay. So another important thing is that if our flow is irrotational, so irrotational basically means that there's no rotation in the flow. So we went over this kind of briefly when we did fluid kinematics. But the way that you can kind of visualize irrotational flow is that if you have your flowing fluid, if you stick some kind of rod or some kind of stick into the flow, and then the way you can tell it's irrotational is the stick will kind of go with the flow, but it won't actually rotate itself. So it'll maintain its same orientation, but it'll just translate. So if the flow is irrotational, then what that tells you is that the vortex lines do not exist. Okay. So just that's kind of in the same way where if you have flow that's at rest, where the velocity is equal to 0. So when you have a flow at rest, then the streamlines don't exist. So if you have a flow that's irrotational, that's kind of the analogous situation, then the vortex lines won't exist at all. Okay. All right. So just like we can have, with velocity, we can have kind of a concentration of velocity within kind of a tubular structure. So you can have basically flow that's in a pipe. You can also have that with vorticity. So we call those vortex tubes. Okay. So we have basically kind of a concentration of vorticity that's in a tube like this. Okay. Okay. And so kind of the properties of this tube is that just like in pipe flow, where we can't have velocity that kind of goes outside the pipe, the same thing here. So on the lateral surface of the vortex tube, there's no vorticity lines that pass through it. Okay. All right. So that's kind of just a quick overview of vorticity kinematics. So there's any questions on this? Right. So the question is, what is the use of vortex tubes? So vortex tubes is kind of just, all of these things are kind of just ways to kind of to visualize this. So actually, so vortex tubes is kind of just, it's a way to kind of express kind of a concentration of vorticity, kind of within kind of a small area. So you have kind of like a whirlpool that's going on where you have kind of a very, obvious concentration of vorticity in a local area. You can use the vortex tube to basically kind of sum up, or to basically kind of, basically use that to kind of visualize all the vorticity that's happening within that whirlpool or something like that. Yeah, so it's a visualization tool. We won't go too much into the mathematics behind it because it gets a little bit intense, but it's, we can kind of think of it as just kind of a way to visualize kind of a concentration of vorticity. All right. Any other questions on this? Okay. Okay. So in addition to vorticity, there's another quantity that we can associate called circulation. Okay. And so to kind of define this, we'll kind of draw another analogy with velocity. Okay. So velocity, one thing that we deal with a lot, especially in like lubrication theory, is we deal with the flow rate, right? Okay. And then the way that we compute that is we basically integrate our velocity over some area. Okay. And then the way that we interpret this usually is that we say that this Q, or this flow rate, it kind of represents a flux of velocity through a surface area. Oh, so the word I'm defining is, this is kind of the topic of circulation, but to kind of define that, I'm drawing an analogy with flow rate. Okay. So we can do the same thing with vorticity. So vorticity, we can take it and we can integrate it. Okay. And the result of this is defined as the circulation. Okay. So this capital gamma right here is going to be the integral of vorticity over an area. Okay. And that's going to give you the circulation. With this omega right there, that's the same as vorticity. Okay. Right. So this kind of goes back to the vortex tube. So when we have pipe flow, we can integrate the velocity over the cross-sectional area of the pipe to get flow rate. So in a similar way, we can integrate the vorticity over the cross-sectional area of a vortex tube, and then that's going to give us the analogy of a flow rate, which is circulation. Okay. Circulation, which is the flux of vorticity. Okay. So for this class, we're going to be mostly focused. This is a class on viscous fluid flow. So what we're interested in a lot is, how does viscosity kind of relate to a lot of these quantities. Okay? So just to kind of give you a preview of kind of where we're going, we'll see that viscosity plays a very important role, and that viscosity can actually produce vorticity. Okay. So we'll kind of see how that is when we go over Kelvin's circulation theorem. But also, just like with a velocity, so we saw that viscosity plays a role in that it helps to basically transport momentum, right? So we saw that with Stokes' first problem, Stokes' second problem. So we see that viscosity has the same kind of effect on vorticity. So vorticity can also be transported through or diffused through the viscosity. Okay. So that kind of does it with kind of the introduction topics to vorticity. So basically, the game plan from here is that we're going to go over kind of the two basic vortex flows, which is the idealized vortex and solid body rotation, and we'll do a practice problem with that. And then we'll go over some of the more fundamental theorems like Kelvin's circulation theorem, Helmholtz vortex theorem, and also the vorticity equation, believe it or not. All right, any questions on this introduction stuff before we move on to the basic vortex flows? Okay, let's go ahead and wipe the board. Okay, so the next thing we're going to do is basic vortex flows. So, first thing that I'll note before we move on for this is that because, we're dealing with rotation, kind of the best coordinate system to do this is in cylindrical coordinates, right? Or in this case, polar coordinates. So like we mentioned before, there's two kind of basic vortex flows that we can go over. So the first is solid body rotation. So the way that we'll characterize solid body rotation is we'll characterize in terms of its u theta. Remember, u theta, that's the velocity component that's in the theta direction, so the one that's kind of rotating. Okay. 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 So that's the formula for the velocity for solid body rotation. So it's defined in terms of the vorticity. So the thing about solid body rotation, that it has a kind of a constant vorticity all throughout its area. So we define it as omega times r divided by 2. Okay, where r here is our variable. Okay. So what this tells us is that as we go radially away from the center, then our velocity is going to increase. So the way that you can visualize this is you can think of a kind of a turning a record player. Okay. So basically, you can think of any kind of cylindrical solid body that's rotating. Okay. Okay. And then the velocity vectors our velocity is going to vary or increase linearly as we get away from the center. So at the center, even though I drew it extremely poorly, we have a velocity of 0 there. And then as we kind of go away from that, our velocity is going to increase. And the rate at which we're going to be increasing is proportional to the vorticity. Okay. Right, so that's solid body rotation. So the other basic vortex flow is the idealized vortex. Okay. So the ideal vortex is kind of opposite. So you can see the R right here is in the denominator. Okay. So in the ideal vortex, our velocity is going to decrease as we move away from the center. Okay. So if we draw this out, it might look something like this. Okay. So our velocity actually, in kind of a pure kind of idealized vortex, we have a singularity of velocity at the middle. So you can see if we have plug in r is equal to 0 here, we get infinite velocity. So most of the time that doesn't happen. So whenever we use an idealized vortex, we kind of ignore the center. Or we use a device called a Rankine vortex, which hopefully we'll get to at the end of today. Okay. So it's going to be maximum near the center. And then as you get away from that, then it's going to decrease. So the plot looks something like this, where you have kind of a maximum, and then as you get away, it starts to decrease, where eventually it reaches kind of 0. All right, any questions on just the definitions of these vortex flows? Okay. Okay. So let's talk about stresses. Okay. So let's start with the solid body rotation. Okay. So if you we're not going to derive it here, but what tends to happen with solid body rotation, since the entire fluid kind of rotates as if it's a solid body, you have basically no shear stresses that occur between fluid elements. So every fluid element kind of sticks within the same kind of orientation. It's flowing like that. Okay? So what tends to happen with solid body rotation is that you have no viscous stresses in the fluid. Okay. So if you actually, take the Navier-Stokes equations or the conservation of momentum equations in cylindrical coordinates, and you plug in our velocity u theta from the previous slide, then you'll see that everything that has viscosity in front of it will go to 0. Okay? And this, of course, assumes that you have no radial velocity and no velocity in the z direction either. And so if you actually do that, you actually plug in your velocities into the Navier-Stokes equations. In particular, the R and the Z components. You'll be left with the following equations. Okay. Okay. So NS here stands for Navier-Stokes. Okay. So we got two equations here. So you have minus rho times u theta squared all over R is equal to dp dr. Okay. So this is the equation that results when you plug in our u theta into the Navier-Stokes. So most of the things will cancel except for these two terms. Okay. So that's the what happens when you plug in an R, and then in Z you also get something. Okay. So you get dp dz is equal to minus rho g. Okay. Which basically represents kind of just the hydrostatic pressure pressure difference as you go down in the fluid. Okay. So in this case, we're interested in the pressure. Okay. So if we take our u theta from before, okay. So we know for solid body rotation, our u theta is given by that expression there. So omega r divided by 2. Okay. So we plug that in. We can basically integrate these two equations at the same time and solve for p. Okay. Okay. So we can basically solve for the pressure distribution as a function of r and z. Okay. And what we get is the following. So we get p of r and z is equal to 1/8 times rho times the vorticity squared, r squared, minus rho g z plus p naught. Okay. Okay. So from this, we get an expression for how the pressure varies in a fluid that's undergoing solid body rotation. Okay. So kind of the key term here is this r squared. So whenever you have an r squared, you know that that's a quadratic term. So that means if we plot the pressure distributions, we're going to get a parabola. Okay. Right, and then that kind of explains some really interesting effects. Does someone have a question?
Yeah. After the box, we can't see what's under there. The page is cut off. Can you move it up?
Let's see. So underneath, you can't see underneath anything that?
Yeah.
Oh, okay. So that all this says is just parabola.
Okay.
Yeah.
Thanks.
That's good to know because normally the my control panel for like highlighters and stuff like that's on the bottom, but I moved it to the top. But if you guys can't see anything down there, I'm going to put the control panel back on the bottom. Yeah. Thanks for telling me. Okay. Any questions on this board before I wipe it? Okay. So actually, let's take that expression and let's assume that P is a constant. Okay. So if we assume that P is a constant, we can solve for Z. Okay. So if we do that, we get Z is equal to omega squared R squared all over 2G minus P naught all over rho G. Okay. So why is this important? So you know what we basically solve for here is what this represents, this Z, is this represents kind of the 8G. Yes, thank you. Okay. This represents basically the curves of constant pressure in a spinning fluid. Okay. So we take kind of an example, right? So say we have kind of a cylindrical vessel like this, right? And say that we're spinning the fluid. Okay. So you can imagine that this is like your coffee cup in the morning, and you're basically spinning it with your stirrer. And then you know for some reason after your milk is stirred in, you keep stirring it. Okay. And so what you should notice is that the surface of the fluid kind of forms a parabola, which looks like this. Okay. So what happens when you keep stirring your coffee like that? Then the fluid kind of assumes kind of the rotation of a solid body. So when it's rotating as a solid body, then we can apply the formulas that we just went over just now. Okay. So what this tells you basically is that this parabolic surface on top of the fluid, okay, everything on the surface here is at constant pressure. In fact, you know, the pressure that is going to be set to is that this is set to be the same as atmospheric pressure. Okay. So basically, in order for the fluid surface to maintain kind of static equilibrium with the atmospheric pressure, then it has to form this parabolic shape in order to do that if it's spinning. Okay? So if you have kind of, you know, you can try this out at home. So you have just a cup of water, you can just stir it for a while, and you'll see that it forms this this kind of iconic parabolic shape, and that's so that you know it can stay in equilibrium with the environmental pressure. All right, any questions on this before we move on to the idealized vortex? Okay. So we can kind of run through the same activity with the idealized vortex and kind of determine what are the lines of constant pressure with an idealized vortex. Right. So let's try idealized vortex. Okay. Right. So if you kind of remember, we looked at the idealized vortex already. So this was kind of a problem in homework 1. Okay. So if you remember from homework 1, we know that in the idealized vortex that we do have some viscous stresses. Okay. So it's a bit different from the solid body rotation. So in solid body rotation, remember, we didn't have any viscous stresses just because of, you know, there's no shear that happens in solid body rotation. But because we have this kind of velocity profile that drops off pretty rapidly, we do have some viscous stresses. We do have some viscous stresses here. Okay. So if we actually compute it, so in particular, there's basically only one component of the viscous stresses, and that's going to be the component r theta. So if we compute that, it's going to be equal to this. Right. So our viscous stress is going to be minus mu times the circulation time over pi r squared. Okay. So if you can actually, look back at your homework one, you can actually, this is kind of what we computed too. The only thing is we multiplied this by the viscosity to compute the viscous stresses. Okay. But the interesting thing about the idealized vortex is that even though we have viscous stresses, turns out that the net viscous force on a fluid element is actually 0. Okay. Right. So to kind of show this, we can plug it into the viscous term of the theta momentum equation. Okay. Okay. So that viscous term is given by this expression here. So we have mu times 1 over r ddr of r du theta dr, okay, minus u theta over r squared plus 1 over r squared times d u theta d theta squared plus 2 over r squared dur d theta plus d squared u theta d z squared. Okay. So if you look at the Navier-Stokes equations in cylindrical coordinates, this is kind of the last term which relates to viscosity. Okay. So if you plug in our u theta, so our u theta in this case, remember, was circulation over 2 pi r. So if you actually plug that into this equation, you'll see that actually everything cancels out. So actually these terms will cancel just because we know that there's no ur, and actually u theta is not a function of theta, so that derivative is equal to 0. And it's also not a function of z, so that term cancels out. And if you plug in this u theta into these two terms, you can see that they're going to be equal in magnitude and opposite in sign, so they're actually going to cancel each other as well. Okay. So with that, we can basically say that the net viscous force is going to be 0. Okay. And so what we can do is we can solve for the pressure distribution in kind of the same way as we did kind of with the solid body rotation. All right. Any questions on this before we move forward with the pressure computation? Okay. Okay. So if we kind of run through kind of the same thing we did before, where we get the equations for the pressure in the r component and the z component, and we integrate that and we combine the equations, we get the following expression. Okay. Right. So we get P of r and theta is equal to minus rho circulation squared over 8 pi squared r squared minus rho gz plus p naught. Okay. And then just like we did with solid body rotation, we can solve for z since we want to get the curves of constant pressure. Okay. We get z, which is equal to minus lambda squared over 8 pi squared r squared g minus p of r theta minus p naught all over rho g. Okay. And what's unique about this curve is that we have the r squared in the denominator here. So these are hyperbolas. Okay. So we kind of sketch it out. It might look like this. Okay. So it looks basically like your bathroom drain. Okay. So this is the lines of constant pressure. So in this case, this line here is in equilibrium with the atmospheric. Okay. So the important thing for the idealized vortex is that even though we have viscous stresses, but the net viscous force is actually 0. Okay. All right. Any questions on this? Okay. So the last topic, since we're almost out of time, I'm just going to introduce it. Okay. So and that's it's called basically a ranking vortex. Okay. So a ranking vortex is basically going to be a combination of the two basic vortex flows that we just went over. So it's going to be a combination of both the solid body rotation and the idealized vortex. Okay. Because remember what we talked about before, an idealized vortex can't kind of exist by itself because we have that 1 over the r. So we can't have that singularity of velocity at the origin. So kind of the most common way that idealized vortices happen in nature is that you have kind of a core where the core consists of fluid that's rotating as a solid body. And then outside that core, we have an idealized vortex. Okay. So a ranking vortex kind of has two parts. So the first part is a core of fluid rotating as a solid body. Okay. And then the second part is outside the core, we have basically an idealized vortex. Okay. So schematically, it looks something like this. Okay. So here's our core. So it's rotating with some angular velocity or vorticity omega. Okay, so inside that core, we have solid body rotation, and then outside, our fluid will be drawn into motion, and the motion will be an idealized vortex. Okay. So mathematically, it looks something like this. Okay. So you have basically a two-part function. Okay, so inside the core, so the core will have a radius of big R. Okay, so inside the core, where R is less than big R, we have solid body rotation, so we have omega R over 2. Okay, and then outside, we have an idealized vortex, which is given by this function here. Okay. So we have omega R squared divided by 2R, R is greater than big R. Okay. Okay. So we have a solid body rotation inside and then idealized vortex outside. Okay. And so where we're going to pick up on Wednesday is that we'll see that ranking vortices are actually common ways to model a tornado. Okay, so that's all we got time for today. So we'll pick this up on Wednesday. Okay, so make sure you you take a look at homework 3. So if you have, so make sure you take a look, and then we'll spend down the first part on Wednesday to kind of review that, or answer any questions you have on that. And then make sure you look at the study guide for the second midterm, which is posted online too, to kind of help you kind of start preparing for that. So remember, the date for the midterm is going to be pushed back to the Monday following, just so we have enough time to finish up Vorticity and to review as much as we need. Okay. And with that, I will see you guys on Wednesday. So stay safe and stay healthy, everybody. And hope you guys have a good night. All right, so office hours. So office hours tomorrow will be in the evening. So the office hours will be 5:30 p.m. to 7 p.m. But most of the day I'm just sitting here at this desk in my apartment. So if there's another time that works better for you, just shoot me an email and we can set up kind of a private meeting. We can talk kind of anytime tomorrow. Yep. Yep. So the only time I'm not available is 4 to 5:30, which is when I'm doing another lecture for another class. But besides that, just shoot me an email. We can talk anytime. All right. All right, if there's no more questions, I'm going to close the meeting. So I'll see you everyone on Wednesday.